The flight deck of an aircraft carrier, according to the unanimous opinion of many military experts, is considered one of the most physically dangerous workplaces existing on the planet, in conditions that are not formally related to direct combat operations. Jet fuel, ammunition, afterburning engines, and electromagnetic catapult and dozens of people working in close proximity to all this at the same time create an exceptionally high risk of fire, and any delay in responding to such a threat can lead to catastrophic, often irreversible consequences for the entire ship. That is why a specially trained and equipped team of deck firefighters is constantly on duty on board each aircraft carrier, ready to respond to a fire within seconds of its detection, regardless of the specific location of the incident on a vast area of the flight deck. The specifics of firefighting on an aircraft carrier differ significantly from conventional coastal firefighting for several fundamental reasons. Firstly, this is an extremely limited space and the highest concentration of potentially dangerous objects in a relatively small area. Neighboring aircraft, filled with fuel and, often, equipped with real military weapons, are located literally a few meters from each other, which creates a serious risk of rapid spread of fire or, what is even more dangerous, detonation of ammunition on neighboring aircraft if the initial fire is not responded quickly enough. Secondly, this is the specificity of the combustion of aviation fuel, the physical properties of which we talked about earlier. Although kerosene itself is relatively resistant to ignition compared to gasoline, once ignited, burning aviation fuel creates an extremely intense, rapidly spreading fire, requiring the use of specialized fire-extinguishing compounds other than ordinary water, which may be ineffective or even dangerous when extinguishing certain types of fuel fires. Deck fire crews are equipped with special heat-resistant protective equipment that can withstand extreme temperatures for a certain period of time in the immediate vicinity of an intense fire, allowing them to get close enough to a burning aircraft to effectively apply fire-extinguishing agents, rather than operating solely at a safe distance. A key role in extinguishing fires of this kind is played by a special foam based on fluorinated surfactants, which can effectively block the access of oxygen to burning aviation fuel, suppressing the fire much faster than using ordinary water. The flight deck of an aircraft carrier is equipped with an extensive system of stationary foam generating units that can almost instantly cover a significant area of the deck with a protective layer of foam if a serious fire is detected. In addition to directly extinguishing the fire, the critical task of the deck fire brigade in the event of a serious incident becomes the fastest possible evacuation of neighboring aircraft and personnel not yet affected by the fire from the immediate danger zone, as well as, if necessary and if appropriate, the emergency release of the aircraft from military weapons or, in a critical situation, the forced discharge of burning or potentially dangerous equipment overboard to prevent detonation and further spread of the fire throughout the deck. Regular, realistic firefighting exercises are an integral, mandatory part of the training of every aircraft carrier crew member, regardless of his primary specialty, since in a real critical situation, every pair of hands that can effectively help localize and extinguish a fire before the situation gets out of control can count. We have already discussed the general principle of aerial refueling. But behind this jewelry operation there is a specific person, whose profession remains one of the most unusual in all of military aviation, a boom operator, who works not sitting in an ordinary chair, but lying face down in a special compartment in the tail of the tanker aircraft. In the tail section of the KS-135 there is a small glass-enclosed cabin, where the operator sits almost on his stomach, looking down and back through a large observation window, watching the approaching aircraft, which comes in to refuel. It is the operator, and not the tanker pilot, who directly controls the boom itself, with the help of special small steering planes at the end of the boom and a telescoping mechanism that allows it to be lengthened or shortened by several meters. The operator directs the end of the boom exactly into the receiving hole on the fuselage of a suitable fighter, compensating for the slightest mutual vibrations of both aircraft arising from turbulence and inevitable micro-oscillations in a dense formation flight. This requires exceptional spatial coordination and constant, intense concentration. The operator simultaneously monitors the exact relative position of the approaching aircraft, controls the boom through a special small joystick, monitors the readings of instruments that control the fuel transfer process, and maintains voice communication with the pilot of the refueling aircraft, adjusting its position if necessary with small voice commands. Refueling is particularly difficult in conditions of poor visibility, at night or in turbulent weather, when visual control of the relative position of both aircraft is significantly difficult, and the slightest mistake can lead to damage to both the refueling boom and the receiving device or even the skin of the fighter being refueled. Modern systems make this task much easier compared to the first decades of operation of such equipment. Many tankers today are equipped with a remote visual surveillance system, RVS, where the operator controls the refueling process not through direct visual observation through a glass compartment, but through a camera system with a three-dimensional stereoscopic image displayed on a special helmet or screen, which allows the operator to be placed in a more comfortable and protected position inside the main fuselage of the aircraft, instead of an extremely uncomfortable one. Isolated tail-prone position, characteristic of older generations of tanker aircraft. Nevertheless, the fundamental task itself, the extremely precise, exquisite alignment of two aircraft moving at high speed at considerable altitude, transferring thousands of liters of combustible fuel under pressure between them through a rigid mechanical connection, remains one of the most psychologically and physically demanding specializations in all of military aviation, the importance of which, for all its apparent stealth, is critical to ensuring the global reach in combat. Effectiveness of all modern air forces. We have already examined in detail high-precision guided weapons, such as the JDEM system, which is capable of independently adjusting its trajectory after being released. But even an ordinary, unguided aerial bomb, devoid of any guidance system of its own, after being separated from the aircraft, hits the target far from randomly. The accuracy of its use is ensured by complex ballistic calculations performed by the aircraft's onboard computer even before the moment of release. The problem that such a ballistic computer solves is much more complicated than it might seem at first glance. A simple bomb thrown from a height continues to move not in a straight line downwards, but along a complex ballistic trajectory determined by several interacting factors. Firstly, this is the initial speed and direction of movement of the carrier aircraft itself at the moment of release. The bomb, having separated from the aircraft, by inertia continues to move in the same direction and with the same horizontal speed that the aircraft had immediately before the release, gradually losing this horizontal speed under the influence of air resistance, while simultaneously gaining a vertical speed of fall under the influence of gravity. Secondly, this is the aerodynamic air resistance acting on the specific shape of a given type of ammunition, which significantly slows down its horizontal movement as it falls, and this relationship is non-linear and differs for each individual type of aerial bomb, depending on its specific geometric shape, mass and distribution of this mass. Thirdly, current weather conditions are of significant importance. The speed and direction of the wind at various altitudes between the aircraft and the ground, which are capable of significantly blowing a falling bomb away from the original vertical projection of the release point, and the wind at different altitudes can have completely different directions and intensity. A modern onboard ballistic computer takes into account all these factors simultaneously, continuously, in real time, receiving data on the current speed, altitude, course and angle of the aircraft from the inertial navigation system, current meteorological data on wind at various altitudes, entered in advance or received through a data exchange system, as well as the exact ballistic characteristics of the specific type of ammunition used, pre-stored in the memory of the onboard computer by the manufacturer. Based on all this data, the computer calculates the exact, optimal moment of release at which the unguided bomb, continuing to move along a predictable ballistic trajectory without any further participation of the aircraft or guidance system, should hit a predetermined ground target. In this case, the pilot is usually shown a special visual indicator on the aiming display, often in the form of a moving ring or crosshair, indicating the calculated point of impact of the bomb at the current flight parameters, which allows the pilot to either wait for the automatic reset by the computer itself, or to independently reset manually at the moment when the indicator is combined with a visually observed target. Even with the most accurate calculations of this kind, an unguided bomb remains a significantly less accurate weapon compared to modern guided munitions, precisely because any unaccounted for or inaccurately measured variable, a sudden gust of wind, a slight deviation of the actual aerodynamics of a particular piece of ammunition from the average calculated values, can lead to a noticeable deviation of the point of actual impact from the calculated one, while a guided munition is capable of independently correcting such a deviation already during its own flight after separation from airplane. There is another extremely highly specialized and little-known category of military specialists whose work is critical to supporting air operations in the most difficult conditions: combat controllers, an elite special operations unit of the U.S. Air Force, whose main task is to create and maintain the operation of improvised, often temporary airstrips in the most inaccessible and dangerous conditions, including territory controlled by the enemy. Imagine a situation where a large military unit urgently needs to deliver heavy equipment or reinforcements to a remote, inaccessible area that does not have any prepared, official aviation infrastructure, no equipped runway, no air traffic control system, no navigation aids to ensure the safe landing of a transport aircraft. It is in such a situation that combat controllers come into play. These specialists, who are fully qualified as certified air traffic controllers, are dropped into the target area, often by parachute, including the previously mentioned high-altitude stealth landing technique, and sometimes by helicopter or by land as part of a larger special operations unit in advance of the arrival of the main transport aircraft with personnel and equipment. Their first task on site is to assess and, if necessary, provide minimal engineering preparation for a potential landing site, be it a natural flat piece of terrain, an abandoned civilian runway, or even a straight section of road that can support the weight of a landing military transport aircraft. The second, critically important task is the installation of the minimum required set of navigation and communications equipment that allows approaching transport aircraft to safely find a given site and perform an accurate landing even in poor visibility, at night or in adverse weather, without any other fixed navigation infrastructure in the area. The third task is the direct control of air traffic at a given temporary site, similar to the work of a conventional air traffic controller, but often performed in conditions of an active threat from the enemy, coordinating the sequence and safe landing and takeoff intervals of numerous transport aircraft delivering personnel and equipment to a given area. Combat controllers also often perform functions that overlap in many ways with the previously described JTAC role, directing air support directly to enemy positions when the appropriate combat need arises in their area of deployment. Combat controller training, in addition to a full, officially recognized air traffic controller qualification, includes intensive physical training and combat skills comparable to that of elite special forces units, as these specialists often operate in isolation from the main force, in a potentially hostile environment, where their own safety and ability to complete the assigned mission is largely dependent solely on their own combat and physical training. It is thanks to the work of such specialists that modern air forces are able to launch full-fledged air operations literally in an open field, where just a few hours ago absolutely no aviation infrastructure existed. For several decades now, several times a year, the exercise known as Red Flag has been held at Nellis Air Force Base in the Nevada desert, considered one of the most realistic and intense Air Force combat exercises in the world, the importance of which for the actual combat training of aircrew cannot be overestimated. The history of these exercises is directly related to the painful analysis of the statistics of air battles conducted by the American Air Force during the Vietnam War. This analysis revealed an extremely alarming pattern. The vast majority of losses of American aircraft in real air battles occurred in the first few combat missions of a particular pilot, while pilots who successfully survived the first 10 or so combat encounters subsequently demonstrated significantly higher chances of survival in further battles, having accumulated sufficient practical combat experience. From this observation was born the concept that formed the basis of the red flag exercise. If real-life combat experience is so critical to a pilot's survival and effectiveness, it is necessary to create the most realistic simulation of such experience before the pilot first encounters a real enemy in a real conflict, thereby, as it were, giving each pilot those critical first few conditional combat sorties in a training environment, rather than in a deadly real combat environment. Red flag exercises feature an exceptional degree of realism in the simulated combat environment. The role of the mock enemy is played by specially trained units of the aggressor, who have studied in detail and practiced the real tactics, weapons and characteristics of potential opponents, often using specially purchased or recreated enemy equipment, or converted and specially tuned own aircraft, simulating the flight and tactical characteristics of specific types of enemy fighters. In addition to direct air countermeasures, the exercises include a full-scale simulation of enemy ground-based air defense systems. Real, albeit training-tuned radar stations and training launchers of anti-aircraft missile systems are used, as realistically as possible, simulating the dense, multi-layered air defense system that pilots may have to face in a real conflict. A critically important technical element of the exercises is the Air Combat Instrumental Control System, ACMI, Air Combat Maneuvering Instrumentation, special onboard equipment installed on all aircraft participating in the exercises, continuously recording the exact three-dimensional position of each aircraft in space, its speed, maneuvers, as well as conditional hits and defeats from the used conventional weapons throughout the entire training battle. These data subsequently make it possible to conduct an exceptionally detailed, objective analysis of each element of the past simulated battle immediately after its completion, clearly demonstrating to the pilots their own tactical mistakes or successful decisions, restoring a complete three-dimensional picture of the air battle that took place, which is inaccessible for such a detailed analysis during a normal, non-instrumental training flight. Pilots who have completed the full cycle of red flag exercises, according to the testimony of many veterans of real combat operations, subsequently note that real combat experience, although it remains psychologically fundamentally different in nature precisely because of the real mortal risk, nevertheless turns out to be much less frightening and disorienting precisely due to the previously accumulated experience of participating in such maximally realistic, detailed training scenarios. The ability to quickly transfer significant amounts of troops, military equipment and equipment to the other side of the globe is one of the most important elements of modern military strategy, and a key role in such a transfer is played by specialized strategic military transport aviation, the most prominent representative of which in the American Air Force is the C-17 Globemaster III. Unlike conventional passenger airliners, which are designed primarily to efficiently transport people on the prepared, long concrete runways of major airports, the strategic military transport aircraft is designed with a fundamentally different set of requirements that reflect the real-life needs of military operations. One of the key requirements is the ability to take off and, most importantly, safely land on relatively short, often unprepared dirt runways, which are significantly inferior in quality and length to standard airport runways. This is achieved due to the special design of a powerful, multi-wheeled landing gear, capable of distributing the significant weight of a fully loaded aircraft over a larger area, reducing the specific pressure on unprepared pavement, as well as the use of a special engine thrust reversal system and powerful brakes, which make it possible to effectively brake a heavily loaded aircraft on a significantly shorter section of the runway compared to a conventional civil airliner of the same size. Another fundamental requirement is a spacious cargo compartment, free of intermediate structural elements, with a large ramp at the rear of the fuselage, allowing for rapid direct loading and unloading of large military equipment, including main battle tanks, armored personnel carriers, artillery systems and helicopters, directly under its own power, without the need for specialized, complex loading equipment, often unavailable in unprepared field operations. Airfields. The A-17 is capable of transporting a payload of up to 77 tons over a distance of more than 4,500 kilometers without refueling, which, if necessary, can be significantly increased through the use of previously discussed in detail in-flight refueling technology, theoretically providing the ability to transport heavy military equipment to almost any point on the globe. No less important is the ability of such aircraft to land personnel and equipment directly in the air, without the need to land on the ground at all, from the classic parachute landing of personnel to a much more technically complex system for landing heavy equipment and cargo using special cargo platforms and multi-dome parachute systems capable of ensuring a fairly soft landing of multi-ton equipment without serious damage. The logistics of a large-scale military movement of troops, involving dozens of similar transport aircraft at the same time, is a separate, colossal task of planning and coordination, requiring precise coordination of takeoff and landing schedules, the availability of refueling stations along the route, the availability of a sufficient number of cargo handling equipment and personnel at both the point of departure and destination, as well as ensuring the safety of the entire route from potential threats. It is this ability to quickly, massively transfer significant military forces over long distances that is the strategic capability that fundamentally distinguishes a truly global military power from a regional power limited primarily by the capabilities of land and sea logistics, which are much slower and subject to a much greater number of geopolitical restrictions. We have already discussed in detail how a modern stealth aircraft minimizes its radar and thermal signature. But there is another physical characteristic that is much more difficult to completely camouflage and which can reveal the presence of an aircraft where the most advanced radars and thermal imagers are powerless. This is the sound made by operating engines and the very structure of the aircraft as it moves through the air. Acoustic detection acquires particular tactical significance precisely at low altitudes and relatively low speeds, typical, for example, for helicopters and some types of drones operating in close proximity to ground targets, where radar detection is objectively hampered by the terrain itself, which creates many so-called radar shadows, but the sound of a running engine can spread and reach the observer even from behind such natural shelters. Human hearing, and even more so specialized acoustic sensors, are capable of detecting the characteristic sound of a helicopter engine and the specific, recognizable noise from the rotation of the rotor at a distance of several kilometers in favorable, quiet conditions, which makes acoustic stealth a serious engineering challenge, especially for combat helicopters, which are often forced to operate at low altitude in close proximity to enemy positions. Engineers have developed several approaches to reduce such acoustic signature. One of the most researched methods, used to a certain extent on some modern helicopters, is a change in the design of the rotor blades, reducing the characteristic, easily recognizable slap sound, which arises due to the special interaction of airflows from the previous and subsequent rotor blades during certain flight conditions. A special, more complex blade shape can significantly reduce the intensity of such a recognizable sound effect. Another approach concerns the engine and transmission directly, the use of special sound-absorbing materials and design solutions inside the engine nacelle and transmission compartment, which reduce the spread of the characteristic mechanical noise of a running engine and gearbox to the outside. There are also certain tactical, rather than purely technological, techniques for reducing acoustic signature, for example, specific flight profiles that minimize engine operating time at maximum, noisiest speeds near a potentially dangerous area, or the use of natural terrain and background environmental noise, for example, military equipment operating nearby or the natural noise of wind and vegetation, to partially mask one's own acoustic signature. It is important to understand that acoustic stealth in general remains a much less developed and much less effective area in comparison with radar or thermal stealth. The fundamental laws of physics of sound wave propagation in the atmosphere are much more difficult to control by engineering methods compared to the more narrowly targeted electromagnetic radiation of a radar, which makes sound one of the most persistent, difficult to eliminate unmasking factors for low-flying military aircraft. Regardless of the achieved level of excellence in the field of radar and thermal stealth of a particular aircraft. In the 60s of the 20th century, the American fighter pilot and military theorist John Boyd developed a mathematical concept that subsequently radically changed the very approach to the design of combat fighters around the world, the energy maneuverability theory, which proposed a fundamentally new, much more accurate way to quantify the real combat capabilities of a fighter, going far beyond a simple comparison of the maximum speed or climb rate of specific aircraft. Before the advent of this theory, comparisons of the combat characteristics of various fighters were often based on relatively simple, isolated parameters: maximum speed, service ceiling, rate of climb at the ground, which, taken individually, did not provide a complete, objective picture of the real effectiveness of the aircraft in a dynamic, constantly changing in altitude and speed maneuverable air combat. Boyd's key idea was to view an aircraft's total energy, the sum of its kinetic energy, determined by its current speed, and its potential energy, determined by its current altitude, as a single, interchangeable quantity that a skilled pilot could tactically convert from one form to another during combat, such as by sacrificing speed to quickly gain altitude, or, conversely, diving down to quickly gain speed at the expense of losing altitude. Boyd's mathematical diagrams clearly showed how the ability of a given aircraft to gain or store such total energy varied depending on the current speed, flight altitude and, most importantly, the intensity of the maneuver being performed at the moment, measured in units of g-force acting on the aircraft. Such an analysis for the first time made it possible to objectively, quantitatively compare the real maneuvering capabilities of various types of fighters, not in static, isolated conditions of straight flight, but precisely in the dynamics of real maneuverable combat, where the key importance is not so much the absolute maximum speed of the aircraft, but its ability to quickly and effectively change the direction and speed of movement, while maintaining a sufficient supply of energy for subsequent maneuvers, without losing a critical tactical advantage over the enemy. This theory had a colossal practical impact on the actual design of a new generation of American fighters, developed with direct consideration of its conclusions, primarily on the already repeatedly mentioned EF-15 and especially EF-16, designed purposefully with a priority for the highest possible indicators of energy maneuverability in a wide range of speeds and altitudes for combat use, and not only to achieve the maximum possible absolute speed, as was typical for the fighter concept of the previous generation, largely formed back in the era of early development of supersonic speeds. The legacy of John Boyd's theoretical work extends well beyond the purely technical design of specific aircraft. The related concept of the decision-making cycle, which he developed, known as the OODA loop, observation orientation decision action, subsequently had a significant impact not only on general air combat tactics, but also on broader military and even, in part, business strategic thought, far beyond the purely aviation specifics, which makes Boyd one of the most influential, although relatively little known to the general public, of figures in the history of the development of military theoretical thought of the 20th century. Each military aircraft, despite all the strength of its structure, has a finite, limited service life, determined by the phenomenon of metal fatigue, the gradual accumulation of microscopic damage in the structural elements of the airframe, resulting from repeated load cycles throughout the entire flight life of the aircraft, which has already been partially mentioned when talking about testing aircraft engines. How do military departments monitor the actual technical condition and residual life of each specific, individual combat aircraft, given that the intensity and nature of operational loads can vary significantly from one specific aircraft to another? depending on the nature of the specific tasks it performs? A key role here is played by a system of individual tracking of operational history, maintained separately for each specific production aircraft throughout its entire flight service. Every significant maneuver performed in flight, primarily the intensity and duration of overloads to which the aircraft's airframe was subjected during a particular flight, is recorded by a special onboard structural condition monitoring system, known as a structural fatigue tracking system. This data is accumulated and analyzed throughout the operational history of a particular aircraft, allowing engineers to fairly accurately calculate the real residual airframe life of a given particular aircraft, which may differ significantly from the calculated average indicator determined by the manufacturer for a given type of aircraft as a whole, depending on how intensively and how close to the maximum operational limitations this particular aircraft has flown throughout its history. Fighters that were intensively used primarily for practicing maneuverable air combat with frequent, intense overloads, as a rule, exhaust their airframe design life much faster compared to aircraft of the same type that were used primarily for less intense, relatively quiet transport or patrol missions with minimal overloads. Upon reaching certain, predetermined threshold values of the accumulated fatigue load, a particular aircraft is subject to a mandatory detailed engineering inspection, often including the disassembly of certain critical structural elements for direct visual and instrumental inspection for the actual presence of microcracks not yet detected by other non-destructive testing methods. If signs of critical fatigue where of certain structural elements are detected, the aircraft can be subjected to a capital life extension program, including replacement or strengthening of the most loaded, worn-out elements of the airframe, which can significantly extend the further safe operation of this particular aircraft, although such a program often turns out to be technically complex and very expensive. In individual, most critical cases, when the detected level of fatigue damage to the structure is considered unacceptable for further safe operation, and the economic feasibility of a major overhaul of this particular site is considered inappropriate, the aircraft is taken out of service significantly earlier than the nominal design service life established by the manufacturer for this type of equipment as a whole, despite the formally still valid warranty or design service life specified in the original technical documentation. Such a thorough, individualized system of accounting for the actual operational load of each individual combat aircraft is a critical element of ensuring flight safety, allowing military engineers to promptly identify and eliminate potentially dangerous fatigue damage long before accumulated latent metal fatigue can lead to catastrophic, sudden failure of the airframe structure directly in flight. The famous fighter training program of the U.S. Navy, widely known under the informal name TopGun, and officially called the United States Navy Fighter Weapons School, owes its very existence to the rather alarming statistics of real combat losses recorded in the initial period of the Vietnam War. An analysis of the results of air battles between American fighters and North Vietnamese aircraft in the early years of the conflict revealed a significantly less favorable loss ratio for the American side than initially expected, given the formal technological superiority of American aircraft of that period over the much simpler and seemingly technically inferior Soviet-made North Vietnamese fighters. A detailed analysis of the reasons for such unexpected statistics revealed not so much the technical imperfections of the American fighters themselves, but rather significant gaps in the practical tactical training of flight personnel for real maneuverable close-in air combat. Much of the pre-war tactical doctrine and, by extension, pilot training programs of the period placed a primary emphasis on the use of medium and long-range missile weapons, largely based on the expectation that future air combat would be fought primarily at long range, without the need for the intense, close-in maneuver engagement that characterized earlier eras of air warfare. The reality of the Vietnam conflict refuted such pre-war assumptions. The restrictions that existed at that time on the use of missile weapons at medium range, including both the technical limitations of the missiles of that generation themselves, and, at times, restrictions associated with the difficulty of visually identifying a target as an enemy at such a distance in a real battle, often forced pilots to engage in close, intense maneuverable air combat, for which a significant part of the American flight personnel at that time was significantly less prepared than their own North Vietnamese opponents, a significant part of whose tactical training, on the contrary, was focused precisely on such close maneuver combat. It was in response to this identified critical problem that the TopGun program was created in 1969, a specialized advanced training school, where already experienced, but in need of in-depth tactical training, fighter aviation pilots of the fleet were sent for an intensive, most practical course of training in the techniques of effective close maneuver air combat, including direct practical acquaintance with real flight tactics and the behavior of a potential enemy through training air battles against specially trained instructors who piloted aircraft whose flight characteristics were as close as possible to the real equipment of the potential enemy of that period. The results of the introduction of such in-depth tactical training turned out to be very impressive. The statistics of the ratio of losses in air battles between American and North Vietnamese fighters significantly improved in favor of the American side in the subsequent period of the Vietnamese conflict, which convincingly confirmed the initial hypothesis about the critical importance of in-depth practical tactical training, and not just the formal technological superiority of the aircraft itself. The experience and methodology developed in the original TopGun program would go on to have a significant impact on overall fighter training far beyond just the Navy, including the Air Force's previously detailed Red Flag exercise, which in many ways developed and adapted a similar basic concept of maximally realistic hands-on tactical training at a larger, integrated level of entire Air Force formations, not just individual fighter pilots. Military aviation is more than just a list of impressive technical features. It is a living system, made up of thousands of decisions made by people who have learned from their own mistakes, sometimes the most tragic ones, to make the next generation of technology and the next generation of pilots a little more prepared for what they will face.